Hello, and welcome to a new episode of targz. You know, when you are watching a movie or a show on a streaming platform, and the recommendation you get are not exactly on spot. So the reason is that there may be noise in the training data used for the recommendation system. And so today we look at an approach to get rid of such noise in a paper titled Post-Training Denoising of User Profiles with LLMs in Collaborative Filtering Recommendation. And we have here the author of the paper, Ervin Dervishaj. Welcome, Ervin. How are you?
Fine, thank you. Thanks for having me.
It's a pleasure. And would you like to introduce yourself?
Of course, thanks. So my name is Ervin. I'm a third-year PhD student at the University of Copenhagen. I'm working in the intersection of recommender systems, representation learning, and lately large language models.
Let's jump into the paper. So what is the paper about? Would you like to give us some context?
So I'll give a brief background for the paper, and then I'll introduce a bit what we aim to do with the work. So basically, when we try to build models for recommender systems, we need access to previous data that, or let's say, the history of individual users. Basically, this means having access to different items that the users have consumed in the past. And we call this in recommender system user feedback. And there are a couple of different feedback that we can get from users. One is explicit, where the user probably gives a proper rating to the interaction that they had. For example, 1 to 5 star rating to different movies or on an e-commerce site. But there is also this other type of feedback, which we call implicit feedback. And basically, these are just interactions of the user with the platform, with the recommender system platform. This can be clicks, or you listening to a specific song, or clicking on a specific movie. So the problem stems exactly from the implicit feedback, because by design, by nature, it's quite noisy. For example, if we use implicit feedback from the user to build the recommendation model, and we see interactions with a specific item, for example, let's say we're building a model for ranking items in an e-commerce platform, and we see interactions of the user with specific items, and then we use that signal to build the model. Later on, we might see that the user might give a negative review to that specific item. So while the interaction was something that we would consider positive, the user interacting with the item, basically clicking on it, or even opening the product page, might end up as something negative. So the problem stems from implicit feedback being noisy. And the community and industry in general has moved from explicit feedback to implicit, just because implicit feedback is much more abundant and you have much more access to data.
Okay, so let's say that, I don't know, my wife uses my Netflix account and suddenly I see a lot of recommendation for Korean dating shows. Is this still some sort of noise?
So that is also some kind of another source of noise that might come in the system, and can be other stuff as well. So for example, myself, when I'm eating something, I usually like to pick a TV show to watch while I'm eating. And that's not always something that follows my preferences in general. I just have to pick something when I'm having a quick bite. And of course, that might later on confuse the system, on top of which the recommendations come from eventually.
What is the thesis of the paper? What are the contributions that you're giving with this work?
Given that this implicit feedback is quite noisy, the idea was to attempt denoising the signal. So we start from a noisy signal, we try to denoise it. And we, going through the literature, the existing literature on this, what had been proposed previously was in training denoising. Basically, what this means is that either before or whilst you are trying to learn the recommendation model, you try to also do the denoising of the signal. There are some problems with this approach. For example, if you want to denoise whilst in training, we call that in training denoising, you need to have additional data in order to understand whether the signal that you are inputting to the recommendation model is indeed noisy or not. For example, let's say you are in the context of an e-commerce data set where you have interactions of the users with the different items. You want to know whether that specific interactions later on led to some negative or positive reviews. So you might need additional data on this. I can give another example. Let's say you are in the movie on demand context. Think about Netflix. And yes, Netflix might use the as signal the fact that you did click on a specific TV show, but then later on you just watched the first 5 minutes. They would need to have and log this additional data in order to understand. So this is one way to, let's say, approaching the denoising of the implicit feedback. The other approach is changing somehow your training procedure of the model. And usually that means you change the objective function of your training. Of course, you have to include additional data to do this, or additional signals that you'd incorporate within the training of the model. What we opted to do was approach the denoising from another perspective. Instead of looking to do it whilst in training, while training the recommendation model, we approached it from after the training of the recommendation model, with what we call in the paper post-training denoising. To sidestep the need for additional data, we resorted to large language models. Nowadays, they are almost everywhere, and with the increasing size of the number of parameters, they sort of gain reasoning capabilities and also have this huge parametric knowledge, which is the internal knowledge of the large language models. So in order to do the denoising, we basically ask the large language model, a large language model, to find out within the interactions, the previous interactions of the users, which items sort of pop out as something that the user would not have interacted with.
If I understood correctly, pre-training is more expensive because in this case you will need to basically change the way you train the model, while the way you're doing it with post-training, this is something that you apply on top of it, right?
Yeah, so we have some benefits when you do post-training denoising. First, you don't have to make any changes to the training procedure and the architecture of the recommendation model. And the other good thing is that you can use immediately off-the-shelf existing recommendation models. And finally, you do not need additional data just because we use this parametric knowledge that the large language model has.
So in the paper, you validate this approach, right?
Exactly. The entire idea stems from the fact that when you do think about the normal split of a data set in machine learning, basically you have your training data, you have your testing data, but you also have a validation set, right? So the idea was, of course, we keep apart the testing data because we want to test our approach with that, so that never goes into any part of the training. We use the training data to train the recommendation model because, as I mentioned, we can use any off-the-shelf recommendation model for this approach. So now we have also the validation set, which we know are items that the user has interacted with. So the entire setup for the large language model was to first represent users by their previous interactions. Basically, these are interactions that we take from the training set. And we also give to the LLM the validation set item. And we basically ask the LLM, can it improve the ranking of the trained recommendation model for this specific user on this specific validation item? So you can think of it as we have a trained recommendation model built from the training data, and we also have this validation set, which are items that we know that the user has interacted with. But of course, the recommendation model is not built on top of these. To the LLM, we give the interactions from the training set for each individual user. We also retrieved the ranking by the recommendation model on this validation set item for each individual user. And basically just ask the LLM, can you improve the ranking of this validation item by removing something from the history of the user? That was the entire setup that we used.
What results did you get?
We observed that if we keep the recommendation model as is. We do not retrain it after we identify which items to remove from the history of the user with the large language model. If we keep the recommendation model unchanged, and we just input the updated histories from the user, updated user data, this time cleaned, we observe that we can improve the recommendation performance of the same recommendation model on 3 different data sets. So we focused on different domains in order to sort of see if our find is good generalized. And we saw that we got almost 5% improvement compared to using the existing user behavior. So 5% improvement on one data set and 3% on another data set.
What are the limitations of this approach?
Yeah, so one of the main limitations stems from the fact that we are relying on the parametric knowledge of large language models to achieve this. And yeah, one of the main issues there is that there is a high propensity for the LLMs to hallucinate. So in cases where you ask the LLM to identify items to remove from the user previous history, previous interactions, it would happen sometimes on some specific LLMs and dataset that the LLM would hallucinate. Basically, it would spit out items that indeed do not exist in the user history. But during our experiments, we had to go through some manual cleaning of the output of the LLM.
What are the next steps in this line of research?
Very immediate next step would be to validate this approach with more models, because in this work we focus mainly on the approach, and we just used a collaborative filtering model, a state-of-the-art model in the collaborative filtering paradigm. But now, judging by the fact that the LLM has this parametric knowledge, and it sort of might even know what the movies, in case we are in a video on demand context, it knows about the movies. We want to test this approach also with content-based recommender models. And these models are such that they focus on the content of the different items. And you might see this, for example, on Netflix, when it suggests you specific movies because you watch something else. And this something else is another movie that you have watched. And basically what it's doing right there is trying to match the content of the movies that you have watched in the past with the content of these recommended items. So the idea would be to move from the collaborative filtering approach that we tried in this when we introduced this work, move to content-based recommendation and see whether there the LLMs can provide better and yield better improvements. And a next step would be to try and use this updated history now with existing recommendation model, because here we kept the recommendation model fixed. So we trained it once, and once we do the post-training denoising, we just remove items from the user histories and run again the updated user history through the recommendation model to get new recommended items. Now, supposedly, this new training data is cleaner. So if we train now a recommendation model from scratch with this data, we'll probably see a much better recommendation model.
Very nice, and I'm really looking forward to have better recommendations. Ervin, thank you very much. It was a pleasure to have you here, and it was very interesting to hear about your research and your PhD work.
Thank you very much for having me.
Thank you very much for listening. If you want to know more about this research, check out the link to the paper in the episode description. If you like the content, please consider giving a 5-star review in the platform you're using for listening to the podcast. See you at the next episode of targz.